Today we will start lecture number 8, which deals with mobile radio propagation. This is a new topic, but let us first see what will be the outline for today's talk. We will first summarize what we have learnt so far. Then we will talk about propagation basics. Then we can look at certain properties of radio waves. Why do we use radio waves for transmission? What is so great about radio waves? Of course, to radiate something and to receive back, we need antennas. We will look at certain antenna basics. And finally, we will look at a few of the radio propagation mechanisms. So, this is the brief outline of the talk. Let us begin by summarizing what we learnt so far. We have looked at the cellular concept and the concept of frequency reuse. We have seen that capacity, the number of users that can be supported throughout the system, is of importance, and in order to increase the capacity, we must reuse the frequency spectrum. The same frequency band may be subdivided and distributed over clusters of cell, and these clusters are repeated so as to increase the overall capacity of the system. This is the fundamental concept of frequency reuse. We also saw that as the cluster size decreases, the capacity increases. We have also seen some examples and how to calculate the actual capacity. We have also seen basics of traffic theory and how you can find out the probability of a call being blocked or a call being delayed beyond a certain duration in time. Then we looked at types of interferences, especially co-channel and adjacent channel interference. We also realized that systems can quickly become interference limited. That is, you cannot increase the capacity any further because you are now limited by interference, not by capacity. Therefore, we also looked at certain basic interference mitigation techniques. We looked at co-channel interference in details and learnt how to calculate co-channel interference. Finally, we looked at the adjacent channel interference and how to space out frequency allocation in order to reduce the effects of adjacent channel interference. Finally, we looked at improving capacity as well as coverage. We looked at certain techniques. Some of them are cell splitting, sectoring, microcell zoning, and of course, the use of repeaters. So, this is what we have done so far. What we start today is a little different. We would like to look at the propagation mechanism, what affects it, how do we actually send the desired signal right up to the receiver, and how do we interpret the signals received and get some useful information out of it. First, we start with a brief introduction. The mobile radio channel places fundamental limitations on the performance of wireless communication system. This is a very important point. Wireless by definition is a very hostile environment. We do not have the luxury of a fixed line, copper, or the luxury of a large bandwidth like fiber. We have to deal with the uncertainties of the channel. Coupled with that is multipath propagation, attenuation, scattering, and a host of other problems. Now, the wireless transmission path may either be line of sight, if I am lucky, that is, I have a direct line of sight from the transmitter to the receiver, or I can have a non-line of sight, in which case my signal is actually obstructed either by building or foliage or hills, even cars on the streets. In general, we deal with the non-line of sight situations in our cellular mobile systems. We do not have the luxury to be in direct line of sight with the base station. Radio channels are random and often time varying. This is important. Not only is it random, that is, you can take enough measurements, come up with the statistics to model it, but with time the statistics might change. This is a fundamental issue, how to model effectively a radio channel. And remember, radio channels behave differently in different frequencies. So, for example, the model that I come up with for 900 megahertz frequency band may not be entirely applicable for 2.4 gigahertz band or for the LMDS 28 gigahertz band. It is different. We will realize why it is different. The lambda, the wavelength of transmission, is going to be affected, and how it gets reflected, obstructed, absorbed or diffracted depends on the size of the wavelength. Modeling radio channels have been one of the most difficult parts of the mobile radio designs. This is because when we have to come up with a whole system model, I must plug in the channel characteristics. I should have a reliable channel model so that I can simulate my system before actually implementing it. Remember, mobile systems are expensive systems. I randomly cannot put a base station, measure the power and then decide, look, I didn't do a good job, let me shift the base station because I didn't get enough power. So measurements are carried on. Based on these fundamental measurements, you try to come up with a realistic channel model. Most of the channel models are random, but as we will see, as you move to higher and higher frequencies, that is lower wavelengths, you will have to go to deterministic channel modeling. So random channel models are good for lower frequency bands. By lower I mean 900 megahertz, 1000 megahertz and 2.4 gigahertz, and by higher I mean above 10 gigahertz. Let us now look at some propagation basics. We start right from the start. That is, when electrons move, they create electromagnetic waves that can propagate through space. All of us know that. So we start with a circuit where we make the electron move in a certain fashion so as to generate a certain kind of, hopefully, a sinusoidal waveform. By attaching an antenna of the appropriate size to an electrical circuit, the electromagnetic waves can be broadcast efficiently and on the other end received by a receiver at a distance away. So antenna is our interface between the circuit and the wireless channel. Please remember, the size of the antenna has a lot to do with the wavelength. In fact, many times we measure the size of the antenna in terms of wavelengths. If I deal with a lower frequency band, that is larger wavelength, then my antenna size will be larger and vice versa. So as we are translating to higher and higher frequencies, our antenna size is diminishing. This is good for us. Okay? So as we move to a higher spectral band, my mobile handset will become smaller and so will the antenna inside it. The radio, microwave, infrared and visible light portions of the electromagnetic spectrum can all be used to transmit information. Remember, all of this is wireless. Wireless radio, point-to-point microwave link, infrared links, right, inter-building, intra-building, and visible light, not guided but unguided. Maybe across buildings I can have links which are visible light links. That is also wireless channel. But clearly visible light has to have a line of sight. I cannot have any obstructions. Infrared too must have a line of sight. Yes, microwave gets very highly diffracted if you have scatters around, so it is preferred to have a microwave line of sight link. However, for radio, which is at a much lower frequency than the above three, can propagate without having a clear line of sight. Information can be sent by modulating one of the properties of the waveform. It could be the amplitude, frequency, phase, and these are not the only possibilities. For example, in ultra-wideband, we use pulse position modulation because we have the luxury to send very narrow pulses, and where the pulses are placed with respect to a reference can tell me what kind of bit pattern I am trying to convey. Properties of radio waves. Here are some of the reasons why we would like to use radio waves. They are easy to generate. The technology is 50 years old. We have mastered the technology. They can travel long distances, okay? Usually without line of sight, because the moment we talk about long distances, we should start thinking about non-line of sight. They can penetrate buildings. So, I can sit in the basement and still talk on my mobile phone. May be used both for indoor and outdoor communications. They are omnidirectional, and we can narrowly focus them at higher frequencies. So, we can actually communicate from one satellite to another satellite or from satellite to a base station on Earth because they can be focused at a small point. Let us look at some other properties. The first and the foremost is frequency dependence. The radio waves at higher frequencies tend to behave more like light. That is, they have difficulty penetrating obstacles. They rather move in direct paths, that is rectilinear propagation, and they can get absorbed by rain, fog particles, dust particles, etc. For example, if I am working for IEEE 802.16 metropolitan area network frequencies or frequencies above 10 gigahertz, my propagation will be affected by rain. If suddenly during the transmission there is snowfall or rainfall, then my signal power at the receiving end will go down significantly. This is not the case when I am using my mobile phone. I will not perceive any perceptible drop in the quality of the voice received on my mobile phone, whether it is raining or not. But at the lower frequencies, they can pass obstacles and the power falls sharply as we move away from the source. How the power falls off has already been studied. It depends simply not on the inverse square law formula. It also depends on the path loss exponent, which is related to your density of buildings, whether it is a concrete jungle, whether you have foliage or any other parameter. Subject to interference from other radio wave sources. So, radio waves have a very high probability that some other source is radiating in a closer band, and I have the chances of emissions or even out of band emissions. Let us look at some basics of the mobile radio propagation. So, here I am talking about VLF, LF and MF bands. These are the various frequency bands depending upon what is the frequency you choose. Radio waves follow the ground. So, here let us look at an example. This is a contour of the earth and I have put two towers. Let us not call them base stations. Right now they are just trying to communicate with each other, and what they are trying to do is send some signal and take it back. Usually the surface of the earth is working as a guide. It directs and helps it to propagate. So, please note that the curvature is taken into consideration and still I am able to communicate. On the other hand, at HF, high frequency bands, the ground waves tend to be absorbed by the earth. I do not have this luxury that we saw earlier. So, we use ionospheric reflections. Let us look at the contour of the earth. Here is an ionosphere. It has lot of charged particles, and let us again put two towers, not necessarily base stations, and if they want to communicate, they use this as a reflection. Please note that the ionosphere shown here is not really a continuous band. It has many bands from which the waves can be reflected. So clearly this path is a multi-path propagation. The reflection here is not through a single reflecting surface. There is a continuum of reflecting surfaces here. So what you receive here is actually a faded signal. Fading, as we will see later on, results basically from multipath. Your signals can reach the receiver not only from a direct path but by reflections. All these signals add up either constructively or destructively and generate something which is entirely different from what you sent. And therefore, you tend to get something called as a faded signal. We will talk about fading and types of fading in later lectures. The problem with HF band is when you transmit it and it hits the earth, it gets absorbed. So I have no choice but to direct my antenna upwards, go through a reflection and come back. A lot of defense applications are still using this HF communication. For VHF, very high frequency, we can have a direct line of sight path. It is important. We have increased the frequency. I do not have the luxury of bending or going through the HF channel. I have to have a line of sight. Of course, it does not get absorbed very much, so whatever goes down hits the earth and is reflected back. Clearly, this can also form a multipath channel, unless of course my antenna has a very narrow half power beam width. That is, it is a very directional antenna. It can only look at a very narrow beam width. In that case, I will filter off most of the reflected waveform. Please note, this is the first time we do not want extra signals to come. Typically, you want the signal power to be as high as possible. Here, I am getting signal through the line of sight and I am getting more of the same signal through reflections. I do not want that, because this signal will reach at a slightly later duration in time and will actually end up corrupting it. Because here I am picking up my signals through an antenna, and antenna gets excited by the electromagnetic radiations and it generates a current. Now, because of the superposition theorem, the first path will generate its own current and the second path will also generate its own current, and these two will interact and there will be a sum, but usually there will be a vector sum which will cause some kind of a fading effect to take place. The signal strength will actually appear to go up or down randomly. So, we must have directional antennas. Remember, there is a relationship between directionality, antenna gain and half power beam width. If my antenna is actually omnidirectional, it radiates on all directions, then antenna gain will be low. Clearly, you are wasting most of the power. You are transmitting in all directions, whereas your intended user is only in a certain direction. Plus, you are trying to listen to the waves coming from all directions, whereas your intended sender is only at a specific direction. So, it is much better to use a directional antenna. In previous lectures, we have seen that directional antennas can be effectively used also to curtail interference. Here, we are putting directional antenna to an entirely different use. Of course, there is a problem with directional antennas. There is no free lunch. The first problem is, if you have a very narrow half power beam width, then it is very difficult to align. Please remember, if you are not aligned, you miss a whole of it. And this is, we are talking about kilometers separation. So, they are separated by several kilometers. So, if they are even off by half a degree here, By the time you reach here, you might entirely miss the beam. The second problem with highly directional antennas is that they have a very sharp cutoff. So, even if because of wind or any other physical reasons the antenna gets vibrated or moves a little bit off center, you are in trouble. So, they are on top of high towers, so they have to be secured very well. The very high velocity winds might move them by a couple of millimeters and you miss the beam. So, directional antennas have both pros and cons. Here in VHF, waves do follow more direct paths. We do need line of sight communications, and as mentioned, the reflected waves do interfere with the original signals, thereby almost corrupting them. Of course, you can recover it back. Modeling the radio channel is typically done in a statistical manner, because we need to have a very good channel model in order to simulate the system that we want to put in place. The statistical modeling is usually done based on measurement data. So, a lot of measurement campaigns are done, wherein you put a power meter in a car or a truck and you move around away from the base station or the transmitter and keep taking measurements. If you are doing indoor measurement campaigns, you put a transmitter on one corner of the room, you put the receiver at different grid locations within the room and take measurements. Currently, an evolving technology is the ultra wideband, where still measurement campaigns are going on, where we actually are trying to collect a lot of data and based on the data figuring out how to model this data. The measurement data is taken based on the intended communication system and the intended spectrum. Both of these two factors will require us to take different sets of measurement data. Measurement data can be taken either in the time domain, that is, we either send a CW continuous wave and try to measure its amplitude, the phase measurements, or the data can be taken in the frequency domain, where you sweep the entire frequency band of interest, collect the data, take the inverse Fourier transform, try to find out the impulse response of the channel. However, at higher frequencies, what do we mean by higher? Above 10 gigahertz, deterministic modeling is more useful than statistical modeling, simply because there are no good statistical model. We cannot take one good statistical model that can explain the behavior at greater than 10 gigahertz. So, we actually do something called as deterministic model and certain techniques such as ray tracing, that you actually trace the rays from the transmitter to the receiver and find out what you actually receive is actually employed. The other thing to note is we can play with the antenna by, say, tilting it or changing its height and change the coverage area. Please note, all of this effort has to do with two things: how far we can send the signal and how reliably we can send the signal. Right? So, we must keep both the parameters in mind. Now, we have seen that antenna form the basic interface between the radio circuit and the radio channel. So, let us look at some antenna basics. The free space received power is given by the free space equation, which is the received power PR at a distance d is related to PT, the transmitted power, times GT, the gain of the transmitter antenna, GR, the gain of the receiver antenna, lambda squared, where lambda is the wavelength, d is the distance at which I am trying to receive the signal, and L is the system loss factor, which has nothing to do with the actual propagation. So, what is important to understand is that the received power depends on a host of things. It is not just the transmitter power. Now, the two factors, antenna gain at the transmitter and receiver are of importance. If I have a very directional antenna, my gain automatically goes up. Unfortunately, for your mobile handsets, you cannot have a very directional antenna because you do not know which way you are facing and where the base station is located. In fact, you must be receiving signals from more than 2 base stations at a time. You have to have an omnidirectional antenna. So the gain of the receiver by design can be only taken to a certain extent, but cannot be increased further because I do not have the luxury of directive antennas. But the gain at the transmitter at the base station, so clearly I am talking about the downlink right now, the gain of the antenna at the base station can be played around with. And usually today we have moved to a domain where we only use directional antennas. Not only it helps us to reduce interference, it gives us a higher gain. The lambda figures in the received power. This is interesting. It tells us that the received power for the same transmit power and antenna parameters would change if I am going to a higher frequency. The higher the frequency, lower the wavelength, the lower the received power. So the problem is that as we go on to higher frequency bands, by definition we are getting lower and more received power. As we move to higher frequency bands, my size of the cell decreases for the same transmit power. This is important to know. In fact, the ultra wide band which I am referring to more than once is working in the 3.1 to 10.6 gigahertz band. It's a bandwidth of 7.5 gigahertz. It's only indoor. It is supposed to work only up to 10 meters. Okay. Of course, there are other related issues. We want the emissions to be at the noise level so that we do not interfere with others. D comes in the denominator, and please note that there is a d squared here because this is the free space formula. This can be replaced by d raised to the power n small n, where n is the path loss exponent, but there are other specific formulas also. L is the system loss factor and has nothing to do with the actual propagation path. We will soon see that this equation holds only under certain conditions. The gain of an antenna G is related to its effective aperture A subscript E, which is defined by gain is equal to 4 pi AE divided by lambda square. Again, the gain is related to the wavelength. Many times the effective aperture is also represented in the units of wavelength. The effective aperture is actually related to the physical size of the antenna. Lambda is related to the carrier frequency by lambda equal to c, the speed of light, divided by carrier frequency f of c. Higher the frequency, the higher the gain for the same sized antenna. So we win some, lose some. Look at the G formula here. Gain is inversely proportional to the square of the wavelength. So for the smaller wavelengths, larger frequency band, the gain is higher. The directivity is higher. We can focus more. Right? So some of the antenna basics. Now let us look at some definitions. An isotropic radiator is an ideal antenna that radiates power with unit gain uniformly in all directions. It's an idealistic definition, but still important because it will help us to have a reference. If we have a directional antenna, maybe we can talk how good or bad it is with respect to this isotropic radiator. It is used as the reference in wireless system. The effective isotropic radiated power was an important parameter which you will see more than once. EIRP is defined as PT, the transmitted power, times the gain of the transmitter antenna. So you cannot just say that look, I have a transmitted power of 10 milliwatts. I would like to know what is the antenna gain. If the antenna gain is more, my effected isotropic radiated power would be more, and vice versa. The effective radiated power ERP is the radiated power in comparison to the half wave dipole antenna. Since the dipole antenna has a gain of 1.64, this can be found out from some basic antenna equations, which is equal to 2.15 dB, the ERP is nothing but EIRP minus 2.15 NdB. Frequently, we would like to code these figures in dB because the free space equation translates into a series of additions. The products become summations. So, dB is a very comfortable way to express these things. In practice, antenna gains are also given in the units of dBi, which is the gain with respect to the isotropic source. So, this small I is for isotropic. So, with respect to the isotropic antenna, I can have a non-isotropic antenna which is a directional antenna. My gain will be better. How much better? I can find out with respect to the isotropic and represent it as dBi. So, if you buy an antenna off the shelf, you will find that maybe the gain is 10 dBi. So, you know what they mean. The path loss represents the signal attenuation as a positive quantity and is measured in dB. So, we are now talking about a transmitter and a receiver which is located at a distance d. Clearly, when you send a signal, what you receive gets attenuated. Path loss is the linkage. So, path loss in dB is nothing but 10 log P transmitted over P received, right? And from the free space equation, it is nothing but minus 10 log GT GR lambda square divided by 4 pi squared d square. Given this, you can find out the path loss in free space. When the antenna gains are excluded, suppose you are using antenna gain of 1 for both the transmitter and receiver, then you simply have the path loss as minus 10 log lambda squared over 4 pi squared d squared. Please note there is a negative sign, so you get an attenuated signal. The free space model is valid only in the far field, also known as the Fraunhofer region. So, you cannot just randomly use the equation anywhere you want to. So, first, before using the free space model, you must calculate what is the near field region, what is the far field region. We will consider how to calculate these. Only then your calculations will hold good. The Fraunhofer's distance is defined by df equal to 2 capital D square divided by lambda. The capital D is the largest physical linear dimension of the antenna. Okay. So, if I have a horn antenna with a cross sectional area which is rectangular, then D will be taken as the larger of the two sides. Okay. If I have a spiral antenna, again I have to figure out what is the largest physical dimension and then use it for your Fraunhofer distance. Addition to that, we must have df, the Fraunhofer distance, much greater than capital D, and df much greater than lambda. So, only when you are beyond the df, if your receiver is farther away from df with respect to your transmitter antenna, can you start using this path loss equations. Clearly, the free space equation that we are talking about does not hold for d is equal to 0. If I am sitting at the base of the base station, well, theoretically I am not at the far field. Hence, in order to have our calculations, we use a close in power reference at a distance d naught. So, now a convenient way to say how much power do I receive, I can do so with respect to a reference distance. The reference distance is chosen such that d naught is still greater than the Fraunhofer distance df. Thus, what we have? The received power Pr at a distance small d is nothing but the received power at a reference distance d naught times log d naught over d whole squared. If my path loss exponent changes to 2.3, maybe I can, as a first level approximation, put 2.3 here, but for the free space it is 2. Sometimes we like to define the received power with reference to 1 milliwatt. Okay. So, the received power at a distance d is nothing but 10 log the received power at a distance d naught normalized with respect to 1 milliwatt plus the path loss we experience from going from d naught to d. So, the units will be in dBm, and here the PR calculation is done in watts. Therefore, I have normalized with respect to 0.001 watts. So, many times when you pick up your mobile phone and if you look at the reference manual, you might see that the receiver sensitivity is minus 100 dBm. Immediately you can find out that with respect to 1 milliwatt, what is the minimum power that your mobile handset can use. Fine. So, in this equation, if you are putting PR in watts and I have put in here 001 W, then the received power is in dBm. So, we have learned so far that we can represent the antenna gain in terms of dBi with respect to reference isotropic antenna, and the received power in terms of dBm, which stands with respect to 1 milliwatt of power. Let us look at some examples. Question is, what will be the far field distance, which is also the Fraunhofer distance, for a base station antenna with the following parameters? What are the parameters? The largest antenna dimension d is equal to 0.5 meters. This is not a very bad assumption. If you walk out and look at one of the base station antennas outside, they typically range from 0.5 meters to 1 meter. The frequency of operation is the GSM 900 megahertz and the case 2 will be 1800 megahertz. So, what we would like to know is what is the far field for 900 megahertz and 1800 megahertz. For the 900 megahertz frequency band, first we calculate the wavelength. Wavelength is nothing but the speed of light divided by the frequency of operation, 900 megahertz, and we get 0.33 meters. They are fairly long waves. In fact, just because they are so long that they can actually bend around the corners, get diffracted, and you can still receive it on your mobile handsets even when you do not have a line of sight. Clearly, these are different from the millimeter wave communication systems, which we will also study in later lectures. Having calculated the wavelength for your GSM 900 megahertz range, we calculate the dF simply as 2d squared over lambda, but d is your largest antenna dimension 0.5, and so you get 1.5 meters, not bad. So, clearly, as long as you are a stone's throw away from the base station, you are in the far field, and all of the equations which we have talked about holds good. What will happen to this 1.5 meters if you now start operating in the other band, which is 1800 megahertz? The other dimensions d is the same. So, first we calculate the wavelength. Frequency is doubled, the wavelength must be half. So, the dF is calculated to be 3 meters. Very interesting. As we go to higher and higher frequency bands, my far field distance moves farther and farther away from the transmitter. But again, 3 meters is not too bad. Yes, question.
Again, for the same amount of gain in the two bands, the size of an 18 megahertz antenna would be much smaller.
Yes, the question being asked is what will happen to the size of the antenna when you move from 900 megahertz to 1800 megahertz, because we have fixed the d, the largest physical dimension, as 0.5. So the answer is yes, the antenna size has to be either optimal for 900 megahertz or 1800 megahertz, cannot be the optimal for both. So most likely you are using a suboptimal antenna which can go from 900 to 1800 megahertz. Clearly the gains will be different and you have to take that into consideration. But as long as my physical dimension d is 0.5 meters, I have no business with the gain. The gain will come automatically when you put in the physical dimension in terms of the effective aperture of the antenna. Those are separate issues. But the distance, the Fraunhofer distance, is dependent only on this largest dimension and the wavelength, nothing else. So this 3 into 10 to the power 8 we are using as the speed of light. Let us look at some more antenna basics. So one simple way to come up with some simple equations is to assume an ideal radiating point. Now of course no antenna is a point, but for the sake of deriving certain basic equations, we can assume that your radiating source is a point source and this has a transmit power Pt and a transmitter gain Gt. It's omnidirectional, so it's radiating in a sphere. Of course you can look at the power flux at a distance d from the radiating source. That is nothing but Pt Gt divided by 4 pi d squared, which is the area here. So that gives you the power flux at a distance d, of course due to an ideal point antenna. Now Pt Gt is nothing but the effective isotropic radiated power. So this is EIRP divided by 4 pi d squared, which can be calculated as absolute value E squared over 120 pi watts per meter squared. Clearly if I put an antenna of the receiver, this power density, the power flux, would generate an electromagnetic field and hence a current, and then I can pick up that current that is generated, amplify it and interpret what was being sent. So let us look at an example. Let us consider a base station, but this time the base station has a transmit power of 10 watts, pretty large, because the base station is on all the time. So if you are going to do a good design, you must ensure that the base station power is as low as possible but should provide enough coverage. The transmission frequency Fc is 900 megahertz again. This time the gain of the transmitter at the base station is 2. So I am talking about a downlink. You are radiating from the base station and you are trying to receive at your mobile handset. So the gain is 2, that is, it has some directivity. That is not too bad. I can put a directional antenna at my base station. But the gain at the receiver GR is 1, kind of an isotropic antenna here. Now the mobile station, which is free to move anywhere in the cell, is at a distance of 5 kilometers. Question being asked is, what is the received power in dBm? Okay. So we use our basic calculations. 5 kilometers is clearly in the far field. We have not talked about the size of the base station antenna here. It can be calculated back using the antenna gain, but we know that 5 kilometers is much greater than that couple of meters which is the restriction on the near field for a base station. So, in the far field, the received power PRD is given by minus 10 log PT GT GR lambda square divided by 4 pi squared d squared. We are now familiar with this equation. We plug in the values. Please note the units: 10 watts. The gains of antennas are dimensionless, 2 and 1. The wavelength is in meters, 0.33 we calculated in the last example, and the distance is again in meters. So, we are dimensionally correct. So, if you do this calculation, you get the received power at a distance of 5 kilometers as minus 92.6 dB watts. Okay. Why do I say this is dB watts? Because here I have put 10 in terms of a watt. But if you want to base it with respect to a milliwatt, then you get an increase of 30. So, you get minus 62.6, because in the denominator you will get 0.001 watt. So, when you normalize it and try to get something with respect to dBm, you get a minus 62.6 dBm. Let us look at another example. I feel this base station power is too high. Let us lower it down. And this distance of the mobile station is also 5 kilometers. Let us talk about bigger cells. So, I move the mobile much farther. So, I would like to explore how much low the received power can become. So, let us look at another example. GSM. Let us have the transmit power at the base station only 500 milliwatts, half a watt. I have drastically reduced that power. Again, I am working at 900 megahertz, same parameters for the transmit and receive antenna. The gain of the transmit antenna is 2, the received antenna is 1. But this time the mobile station has wandered off to the boundary of the cell, which is almost at a distance of 10 kilometers. Normally, we do not have cell sizes larger than 10. So, I am actually looking at a worst case scenario. The question that we want to know is, what is the received power in dBm? We use the same formula. Of course, we expect the received power to be much lower. How much lower? So, use the same formula again. This time I have substituted 0.5 watts, and here the distance has been increased to 10,000 meters, and the received power is minus 111.6 dB watts, which is equal to minus 81.6 dBm. So, can my handset work? Is this a good value? Is it a bad value? Remember, it is 81.6 dB lower than the 1 milliwatt power. Question? Okay. So, the basic question is this good enough? So, we would like to know what is the receiver sensitivity of a standard GSM phone. What is the minimum power level that is required for your GSM phone to pick up the signal and work with it effectively? The answer is, the receiver sensitivity of an average GSM phone is less than 100 dBm. In fact, for a better design system, it can be minus 110 dBm. So, clearly my GSM phone can not only pick this up, but very happily work with this. But remember, these parameters are important to decide what is the size of your cell, what is the link budget, what is the possible coverage. Now, let us briefly look at some radio propagation mechanisms. Yes.
So, in the previous slide, as the phone moves away from the base station, its power will be changing continuously.
Yes.
So, the receiving power of the at the mobile station is also changing.
Yes. So, the question being asked is, as we move away from the base station, clearly the path loss increases, and continuously the power of the received the power received at the mobile station changes. it keeps on going down as you move away. The reverse side is also true. As you move closer to the base station, the receipt power at the base station increases, and we have to take care of the near far problem, as we discussed, that when you go closer to the base station, you have to progressively lower your transmit power to ensure that what the base station receives is just enough, just above the receiver sensitivity of the base station and no more further. I should not radiate too much, because if my received power is much higher than the threshold, then of course I can work with my signal, but I have already contributed to some interference somewhere. So, power control, power monitoring are two key parameters that are taken into consideration while designing any cellular mobile system. Okay. However, when we say that I am getting an attenuated signal, my signal may be coming directly, or it may be coming through a reflection or a series of reflections, or through diffraction, or even through scattering. So, it is important to understand how the signals which emanate from an antenna actually reach the receiver antenna. So, very briefly, let us look at what are the radio propagation mechanisms this time. So, one of the most important one is through reflections. Again, there can be various kinds of reflections. You could have a wave reflected off a metallic source. It could be a metallic reflector, it could be a non-metallic reflector, it could be wood, trees, foliage, or any other thing. Then you have a possibility of scattering. So, you do not have a line of sight, but through scattering you receive the waveforms, or you can even have diffraction across the edges. Now, all these parameters will change depending on which frequency you are working with. So, the radio propagation mechanism is different for different frequency bands. They have their associated problems. So, when you try to look at propagation issues for various bands of frequencies, you have to see whether your problem is arising due to multiple reflections, or diffraction, or scattering, or a combination of all three. So, what are these? Reflection occurs when the electromagnetic wave impinges on an object which has a very large dimension as compared to the wavelength. Everything is with respect to the wavelength. So, the surface of the earth, buildings, walls, large table surfaces, all of them are reasonably large. For 900 megahertz, we know that the wavelength is 0.33 meters. For 1800 megahertz, it is 0.175 meters. So, all of these things listed here are large with respect to the wavelength. Now, what do we mean by large? Typically, I would like to have at least an order of magnitude difference. Okay. So, if I am looking at 0.17 meters, then any object which is larger than 1.7 meters is good enough to be called as large, and a reflection might take place. Diffraction, on the other hand, occurs when the radio path between the transmitter and receiver is obstructed. Clearly, we are talking about the non-line of sight. So, it is obstructed by a surface that has sharp irregularities, for example, edges. So, we live in this man-made world which has lot of objects with sharp edges. So, diffraction is a part of life, and it is very good because it explains how radio signals can travel in urban and rural environments without a clear line of sight path. So, it is good for us. Scattering occurs when the medium has objects that are smaller or comparable to the wavelengths. So, it is an antagonist approach to reflection. In reflection, the object is much larger than the wavelength. Here we are talking about much smaller than the wavelength. So, small objects, rough surfaces, irregularities, water droplets, rain, snow, dust particles, all of them can cause scattering. In fact, when you say smaller, they should be smaller all right, but if it is too small, then the effect may not be perceptible. So the word comparable has been highlighted here. Scattering is prominent when the objects are comparable. Let us look at a millimeter wave, for example. So the wavelength are in millimeter. Raindrops are also of the diameter millimeters. So scattering will be prominent in millimeter wave communications when it is raining. But it will not be so for 900 megahertz, even though the raindrops are much smaller than the wavelength. So all these factors and a combination of them together form why and how a propagation happens. Let us now summarize today's lecture. We talked about propagation basics. We also looked at some of the properties of radio waves, why they form good candidates, what is so good about radio waves that they are being popularly used. We then looked at antenna basics. We looked at the gain, the effective aperture, and how with respect to the antenna gains we can get the received power. We looked at some of the radio propagation mechanisms, which are the reflection, the diffraction, and the scattering. Okay. So we will conclude our lecture here today, and we'll actually look at the details of reflection, refraction, and diffraction, and look at the models for propagation in the next lectures. Thank you.